Hello everyone and welcome back to another video. Happy Pi Day. It is 3:14, at least here currently. And to calculate pi today, I've set up this kind of fun experiment here. We're basically, we have a bucket of water, and as you can see here, I've gotten that out earlier, we have a golf ball. And what we can basically do is drop this golf ball in said water, like so. And you'll notice that it's going to fall slower through the water than, the air, as you would expect. So basically, what we can do is use Stokes Law of drag and calculate pi that way. So Stokes Law of drag basically states that the force of drag is directly proportional to your velocity. And one of those constants in front of the velocity is a 6 pi. So basically, based on that, we can calculate how long it takes for the golf ball to drop through this 8.5 inch-ish bucket of water, and we can calculate pi that way. So let's get to it.
There's no need to take pictures.
So here we have Stokes' law of drag, and you can kind of see what I was talking about earlier. We have this pi here, our constant mu, and our radius, and then our velocity. And what we can basically do here is use this right here in conjunction with what we know from just normal physics, and basically calculate or solve for the differential, or find the differential equation and then solve that to basically find our velocity, then our distance, our displacement at each point in time. So yeah, let's go ahead and do that. So we know that our force of drag is just equal to that, but we also know that our force due to gravity is just our normal mg, right? So this basically just means that our net F net, which is just going to be mass times our acceleration, is just going to be equal to mg, and then minus, I'm just going to call all these constants k for now, just for the sake of, differential equationing, times v. And another way we can write this is just v dot is equal to mg, or sorry, not mg, g minus k over m times v. And this differential equation right here actually really isn't that bad to solve. All we can just do is basically just separate it. So divide both sides by g minus k over m, and we get v dot over g minus k over mv equals 1. Basically meaning that if we were to integrate both sides, we end up getting the integral dv over g minus k over mv equals the integral of t times dt. And the integral on the left, the integral on the right is actually, the integral on the right is actually incorrect. That should just be integral dt. That shut me ahead a bit. Apologies. But the integral on the right is pretty, I kind of already wrote the answer. It's just t plus some constant c. But then the left, it's really not that bad either. All it is just we just have to apply, we could do this kind of more formally doing a u sub, or we just could kind of do it in our head. It's not all too terrible. We're just going to get a natural log term of g minus k over mv. And then we're also just going to get a constant up front because, whenever we differentiate this, we are going to have the chain rule. So to kind of account for that, we're just going to have a minus m over k here. Now all we have to do is solve for v and integrate it again to find our displacement. So multiplying both sides by 1 over this right here, we end up getting minus k over mt plus c, I'm just absorbing all the constants into the c, equals our natural log term, but I'm just going to raise this to the power, of e just to kind of simplify things faster, k over mv. Yes, okay. And now what we have, we can solve for v now. It's not all too terrible. So what we have is just mg over k minus, that's right, okay, mg over k minus m over k e to the minus k over mt, and we're just going to have a constant c out front. And this is our velocity right here, but we kind of do need to solve for this constant c here, because we don't exactly, well, we just need to solve for it. And the way we're going to do that is basically say, in the video, when I drop the golf ball, you will note that I'm not like throwing it up or throwing it down. I'm just kind of dropping it, meaning that our initial velocity is equal to 0, meaning that v of 0 should just be equal to 0. So if we plug in 0 here, I'll do this off to the side. When we plug in 0 here, what we get is mg over k minus some constant c, or really equals some constant c times m over k. And from this, it just kind of follows that c is just equal to g, which is, 10, but like not 10. I'm just going to call it 10, I guess. We'll see what I do in the Desmos. But yes. We end up getting here, I'm going to factor out the factor of mg over k, just for brevity. So what we have then is mg over k times 1 minus e to the minus k over mt. And this right here is just our velocity in terms of time. So then all we need to do now is do one more round of integration. Just kind of getting long, I know. I'm sorry, it's supposed to be a pi day video, not an integration one, but or a differential equation video, but it's okay, I suppose. It's really not that bad. So what we have here, we need to integrate this one more time. So this means that our x is just equal to mg over k times, t, times t. I'm just going to distribute this minus m over g. So minus m g over k, and then times negative m over k. E to the minus k over mt. That way when you differentiate it, you get what you started with. And then we also know that whenever we plug in 0, so when like x of 0, this should really just be our initial height, so I'm just going to call it h naught. Or I guess x naught. I'll do x naught, sure, why not? Haha, fun. But whenever we plug in, plus some constant c, whenever we plug in 0 there, we should end up getting 0. So this basically just means that we have m squared g over k squared plus c must be equal to 0, must be equal to x naught. Again, this just follows from this equation right here. I'm just kind of going through and simplifying some things. So then what we're left with actually is just our constant c is equal to x naught minus m squared g over k squared. Meaning that our position in terms of time is just going to be, I'll write this in a different color now, mg over k times t plus this time m squared g over k squared times e to the minus k over m times t plus, this is getting kind of lengthy, I know, I'm sorry, plus x naught minus m squared g over k squared. And basically what we can do now is plugging everything in, so we know exactly how long it takes for the golf ball to drop. That's our t. We know the mass of our golf ball. We know the force of gravity. The only thing we really don't know is, well, I say quote-unquote don't know. We know everything. The only thing we don't quote-unquote know is pi, because that's what we're trying to solve for. And it basically just lies in this constant k. So all we need to do really is solve for this constant k to determine pi. So yeah, let's pull up the Desmos. Okay, now that we've pulled up the Desmos, what we can do now is just calculate, we can calculate pi, can't we? So what I have here is basically I have all of our values that we need. I should really make this 9.81 if we want to be like, guess more precise. But basically what we have here is our list of values, everything that we could basically possibly need. So we have our constant k right here, which, well, we're assuming pi right here, but I'll actually change that and we'll solve for it. But basically we have our height right here, which is about 8.5 inches. I just converted that to meters because we love units, absolutely. Just they're the bane of my existence. Oh my gosh. Anyways, the radius of our golf ball. But what I did is that I don't really have anything here that I can measure the golf ball by, but I'm just gonna kind of assume that my dad's golf balls are regulation, basically so that the radius is at most that, and the mass is like at most that. So yeah. But to calculate pi, what we're going to do is just take this equation right here, which is our equation for our distance, and all we're going to do is just take this and really just plug in values. So I'm just gonna copy and paste this, make it equal to h. Boop. There we go. Okay. And the only thing we need now is time, right? And from what I measured in the video, the time it takes is about 0.43 seconds. That's how long it took to fall, about. So I'm just going to put T naught in here, just to put it in there. So then all we actually need now is to kind of plug in this thing for K, and then see what decimal spits out for pi. We could always like try to do this not numerically, but I'm gonna be quite frank with you. Solving for K here looks like a nightmare, so we're not gonna do that. We're just gonna let Desmos do some approximating for us, because it's not that bad. So I'm just gonna make every pi just in X, because that way Desmos will actually spit out a number for us. Thank you, Desmos. We love you. Okay. Yeah, just watch this right here, because let's make sure everything is squared. So, what you'll notice here now is that we have everything in terms of pi, or not in terms of pi, over pi's are basically an x now, so that if all you have to do is just, well, I'll make it a different color. All we have to look for is a giant dotted line around 3, and that should be our value for pi. Which, like, it looks pretty promising, right? Like, okay. That's actually not bad. So, apparently, everyone is wrong, and pi is actually 3.0126. So yeah, now that we've concluded that the value for pi stored by everyone else is wrong, no, I'm kidding. I'm just happy we got, I'm actually just happy we got like the same first digit. I honestly didn't expect this to work. But pi is about 3.0126, apparently. Anyways, thank you all for watching this Pi Day special, and I hope all y'all enjoyed. See you in the next one.